Welcome to this lecture on single-atom catalysts. Today we're going to explore one of the most fascinating and counterintuitive developments in catalysis science, how individual metal atoms can outperform their larger counterparts. Before we dive into single-atom catalysts, let's quickly review what catalysis is. A catalyst is a substance that increases the rate of a chemical reaction without being consumed in the process. Traditionally, we've divided catalysis into two main categories: homogeneous and heterogeneous catalysis. Homogeneous catalysis occurs when the catalyst is in the same phase as the reactants, typically both dissolved in a liquid solution. Heterogeneous catalysis involves a catalyst in a different phase from the reactants, most commonly a solid catalyst with gaseous or liquid reactants. Each type has distinct advantages and disadvantages. Homogeneous catalysts have all their metal centers accessible and active, leading to high activity and selectivity. However, separating them from products is challenging. Heterogeneous catalysts are easy to separate and reuse, but only surface atoms are active, wasting most of the metal. For decades, catalysis scientists dreamed of combining the best of both worlds. What if we could have the high activity and atom efficiency of homogeneous catalysts with the easy separation and stability of heterogeneous systems? This is where single-atom catalysts come in. They represent a forbidden combination that seemed impossible until recently. Single-atom catalysts consist of isolated metal atoms anchored on solid support materials. Each metal atom is separated from its neighbors and acts as an individual catalytic site. Imagine a flat support surface dotted with individual metal atoms, each one isolated and spaced apart. Unlike traditional heterogeneous catalysts, where metal atoms cluster together in nanoparticles, here each atom stands alone. Now here's where things get really interesting and counterintuitive. Let me ask you a question. Why would a single atom be more active than a cluster of atoms? Traditional catalysis wisdom tells us that we need ensembles of atoms working together. The most active sites on metal surfaces are steps, edges, and corners, where multiple atoms create special geometric arrangements. For many reactions, we thought we needed multiple surface atoms to bind and activate reactant molecules. How can a single, isolated atom do the job? On the left, we see the traditional view, a nanoparticle with many atoms clustered together. On the right, a single atom with bonds extending outward to the support and to reactant molecules. This single atom somehow must do the work of many. The answer lies in how dramatically the electronic structure changes when you go from a bulk metal or nanoparticle down to a single atom. Let me explain. In bulk metals and large nanoparticles, the d electrons are delocalized across many atoms, forming a continuous band structure. This gives metallic properties, but also limits the binding strength variability. The single atom has discrete, atomic-like energy levels. The d orbitals are localized and can interact more strongly and selectively with reactant molecules, similar to molecular catalysts. Compare the electronic structure. The nanoparticle has a broad, continuous d-band. The single atom has sharp, discrete energy levels. This difference is crucial for reactivity. The coordination environment around the single atom is absolutely critical. This determines the electronic properties and catalytic behavior. Single atoms don't float freely. They're anchored to the support through coordination bonds with surface atoms like oxygen, nitrogen, or sulfur. Here's a schematic showing a metal atom coordinated by 4 atoms from the support. This could be nitrogen atoms in a carbon nitride support, or oxygen atoms in an oxide support. The coordination number and geometry profoundly affect the electronic properties. Let's look at some common coordination environments that researchers have identified. One of the most common is metal-N4, where a metal atom like platinum or iron is coordinated by 4 nitrogen atoms in a square planar arrangement. This is inspired by porphyrin structures in nature. Another common motif is metal atoms bridged to oxide supports through oxygen atoms. The metal might coordinate to 2 or 3 surface oxygen atoms. Defects like oxygen vacancies in metal oxides can act as traps for single atoms, creating well-defined coordination pockets. Here are 3 coordination motifs. Left shows Mn4 in a planar arrangement. Middle shows a metal bridged to an oxide surface through oxygen atoms. Right shows a metal atom trapped in a defect site, surrounded by support atoms. Now let's talk about performance. Single-atom catalysts have demonstrated truly extraordinary activity that seems to defy conventional wisdom. Consider platinum single atoms for carbon monoxide oxidation, a benchmark reaction in catalysis. Let me show you some remarkable data. We measure catalytic activity using turnover frequency, which tells us how many reactant molecules are converted per active site per unit time. Higher is better. Look at this bar chart. 2 nanometer platinum nanoparticles show a turnover frequency around 10. 1 nanometer clusters show about 30. But platinum single atoms show over 150 molecules per site per second. That's a 15-fold enhancement over traditional nanoparticles. This raises a critical question. Why are single atoms so much more active? What's happening at the atomic level? The answer lies in achieving optimal binding energies for reactants and intermediates. Let me explain using the Sabatier principle. The Sabatier principle states that the best catalysts bind reactants not too strongly and not too weakly, but just right. Too weak and reactants don't activate. Too strong and products can't desorb. This is a volcano plot showing activity versus binding energy. The peak represents optimal binding. Nanoparticles often bind too strongly or too weakly. Single atoms, with their unique electronic structure, can hit the sweet spot at the volcano peak. If activity is impressive, selectivity is even more remarkable. Single atom catalysts can achieve near 100% selectivity for desired products. In selective hydrogenation, we want to reduce one functional group while leaving others untouched. Nanoparticles often over-reduce and create unwanted byproducts. Single atoms, with their precisely defined coordination environment, can selectively activate only the target bonds. It's like having a precision surgical tool versus a hammer. Compare the selectivity. Nanoparticles might give 60% selectivity with multiple byproducts. Single atom catalysts can reach 98% selectivity, producing almost exclusively the desired product. Now here's something really fascinating. Single atom catalysts are not static. The active sites are dynamic and can change during the reaction. Under reaction conditions, the metal atom can move slightly, change its coordination number, or even temporarily cluster with nearby atoms. This is called structural fluxionality. Using operando spectroscopy techniques, scientists can now watch single-atom catalysts working in real time and see these dynamic changes. Here we see dynamic restructuring. Before reaction, the metal atom has 3-fold coordination. During the reaction, it adopts 4-fold coordination and binds a reactant molecule. The site adapts to the reaction requirements. The support is not just an inert platform. There are strong electronic interactions between the metal atom and the support that fundamentally alter both. Electrons can transfer between the metal and support, changing the oxidation state and electron density on the metal atom. This charge transfer is crucial for activity. During catalysis, the support can actively participate by donating or accepting electrons, making it a dynamic partner rather than a passive stage. Visualize electron flow. Green arrows show the support donating electrons to make the metal more electron-rich. Blue arrows show the metal transferring electrons back during certain reaction steps. This bidirectional flow is essential. Let me give you an analogy to help understand why single atoms outperform large clusters. Think about workers in a factory. A large nanoparticle is like having a big team of workers, but they're poorly organized. Most workers are buried inside the team and can't actually interact with the work. Only those on the surface edges are useful. A single atom catalyst is like having one highly trained specialist who is perfectly positioned to do exactly the right task. Every single atom is working. There's no waste. The specialist knows exactly what to do and does it with precision. On the left, the nanoparticle team. Many atoms are hidden inside, shown in faded gold. Only the surface atoms in bright gold are active. On the right, the single atom specialist. One atom, perfectly positioned, with all its coordination sites available. Maximum efficiency. Beyond performance, there's a powerful economic argument for single atom catalysts, especially for precious metals like platinum and gold. Precious metals are extraordinarily expensive. Platinum costs around $30,000 per kilogram. Every atom counts. In a typical nanoparticle catalyst, Maybe only 10 to 20% of the metal atoms are on the surface and catalytically active. The rest are just expensive dead weight. With single-atom catalysts, 100% of the metal atoms are on the surface and active. This is the ultimate atom efficiency. Compare atom utilization. For a 5-nanometer nanoparticle, only the small green portion at the top represents active surface atoms, about 15%. The large red region below is wasted metal. For single atoms, the entire bar is green. Every atom counts. If single-atom catalysts are so great, why isn't everything made this way? Let me discuss the challenges that researchers face. The first major challenge is stability. Single atoms want to aggregate into clusters and nanoparticles because that's thermodynamically favorable. Under reaction conditions, especially at high temperatures, single atoms can migrate across the support surface and cluster together. This process is called sintering, and it destroys the single atom structure. Here's sintering in action. We start with 3 isolated single atoms on the left. After heating, they migrate and cluster together into a nanoparticle on the right. This single atom structure is lost. The solution is to design supports with strong anchoring sites that trap the metal atoms. Defects, diopants, and specific functional groups can create energy wells that prevent migration. The second challenge is making and characterizing these materials. It's not easy to create truly isolated atoms and prove that they stay isolated. Synthesis requires precise methods like atomic layer deposition or carefully controlled coprecipitation and calcination. The metal loading must be very low, typically less than 1 weight%. Characterization requires advanced techniques. Aberration-corrected scanning transmission electron microscopy can image individual atoms. Extended X-ray absorption fine structure and X-ray absorption near-edge structure probe the local coordination environment. Not all reactions are suitable for single-atom catalysis. Some reactions genuinely require ensembles of atoms working in concert. Reactions that require dissociating strong bonds, like nitrogen triple bonds, often need multiple adjacent metal atoms to provide sufficient activation. Single atoms may lack the geometric requirements. This raises an important question. Which reactions are ideal candidates for single-atom catalysis? Let me answer that question. Certain reaction types are particularly well suited to single-atom catalysts. Oxidation reactions work extremely well. Carbon monoxide oxidation, alcohol oxidation, and selective oxidation of hydrocarbons all show exceptional performance with single atoms. Selective hydrogenation is another sweet spot. Reducing carbonyl groups or carbon-carbon double bonds while preserving other functionalities benefits from the precise control that single atoms offer. Electrochemical reactions like oxygen reduction for fuel cells and hydrogen evolution for water splitting are outstanding applications. Single-atom catalysts can rival or exceed platinum nanoparticles. Photocatalytic applications like carbon dioxide reduction and photocatalytic water splitting also benefit from single-atom active sites with their tunable electronic structure. Here's a summary of reaction suitability. Green shows excellent candidates like CO oxidation and selective hydrogenation. Yellow shows good candidates that work well but may need optimization. Red shows poor candidates where ensemble effects are critical. Computational chemistry has been absolutely crucial in understanding and designing single-atom catalysts. Let me explain how theory helps. Density functional theory calculations can predict how strongly reactants bind to different single-atom configurations and calculate activation barriers for elementary reaction steps. Before making anything in the lab, theorists can screen thousands of combinations of metals, supports, and coordination environments to identify the most promising candidates. Compare approaches. Pure experimental work involves slow trial and error and is expensive. Theory-guided design allows rapid screening of many possibilities before expensive synthesis, dramatically accelerating discovery. A powerful approach is descriptor-based design, where we identify simple electronic or geometric parameters that predict catalytic performance. The D-band center is a classic descriptor. It tells us about the average energy of the metal d orbitals and predicts how strongly molecules will bind. Higher D-band center means stronger binding. Coordination number is another key descriptor. A 3-coordinate atom has different electronic properties than a 4-coordinate or 5-coordinate atom. The charge state of the metal atom, whether it's electron-rich or electron-poor, dramatically affects reactivity. We can tune this through support choice and coordination environment. Here's a descriptor plot showing binding energy versus d-band center. Each red dot represents a different metal support combination. The trend is clear. Higher d-band center correlates with stronger binding. This lets us predict and design catalysts rationally. Single-atom catalysts are moving from academic curiosity to real industrial applications. Let me highlight some examples. One promising application is in automotive catalytic converters. These devices clean exhaust gases from vehicles. Current catalytic converters use precious metal nanoparticles, primarily platinum, palladium, and rhodium. These metals are expensive and supply limited. Single-atom catalysts can achieve the same emission control performance with up to 90% less precious metal. This could revolutionize the industry and make catalytic converters much more affordable. Fuel cells are another major application. Proton exchange membrane fuel cells need efficient catalysts for the oxygen reduction reaction. The oxygen reduction reaction is notoriously sluggish and currently requires large amounts of platinum. This makes fuel cells prohibitively expensive. Single-atom platinum catalysts, or iron-nitrogen-carbon single-atom catalysts, show much higher mass activity, meaning more current per gram of metal. This could finally make fuel cell vehicles economically viable. Compare mass activity for fuel cell catalysts. Commercial platinum-carbon shows modest activity in blue. Platinum single atoms in green show more than double the activity. Even non-precious iron-nitrogen-carbon single atoms in yellow show competitive performance. Single-atom catalysts are also finding use in chemical manufacturing, particularly for green chemistry applications. Selective oxidation reactions can produce valuable chemicals with minimal waste and byproducts. Single atoms enable this selectivity. Converting carbon dioxide into useful products like methanol or formic acid is a grand challenge. Single-atom catalysts show promise for making this economically viable. Let me conclude by discussing where this field is heading. What are the frontiers in single-atom catalysis? Researchers are exploring what happens when you go from one atom to two atoms, or small clusters of 3 to 5 atoms. Two adjacent atoms can cooperatively activate strong bonds that single atoms struggle with, combining single-atom benefits with some ensemble effects. Here's the progression. Single atom on the left. Dual atoms in the middle, close enough to cooperate. Small 3 to 4 atom cluster on the right. Each configuration offers different properties and possibilities. Another frontier is creating multifunctional sites, where single atoms work together with other active species. Imagine a metal single atom next to an acid or base site on the support. One site activates the substrate, the other performs a subsequent transformation. This tandem catalysis can enable cascade reactions. Coupling single-atom catalysts with photosensitizers or plasmatic nanoparticles can enable light-driven catalysis, harvesting solar energy to drive chemical transformations. Machine learning is accelerating the discovery of new single-atom catalysts at an unprecedented pace. Machine learning models trained on existing data can predict the activity of untested metal support combinations, guiding experimentalists to the most promising candidates. Active learning approaches use iterative cycles where models suggest experiments, results feed back to improve models, and the process repeats. This closed-loop approach dramatically speeds discovery. A critical research direction is understanding how and why single-atom catalysts degrade, so we can design more stable systems. Studying catalysts under realistic operating conditions, not just in idealized lab settings, reveals degradation pathways that can then be mitigated through design. If we understand exactly how atoms migrate and cluster, we can design support architectures and operating protocols that block these pathways and extend catalyst lifetime. Let me summarize this lecture. Single-atom catalysis represents a true paradigm shift in how we think about catalytic active sites. The unique electronic structure of isolated atoms creates binding energies and reactivities impossible with larger particles. This is the fundamental reason for their extraordinary performance. Every metal atom is on the surface and active. This is the ultimate utilization of precious and expensive elements. The well-defined coordination environment and absence of multiple adsorption sites enable exquisite selectivity for desired products over byproducts. Keeping atoms isolated and preventing sintering demands careful support design with strong anchoring interactions. Some reactions genuinely need ensembles of atoms. We must carefully match the catalyst architecture to the reaction requirements. Computational methods, especially combined with machine learning, are enabling rational design and accelerating the discovery of new single-atom catalysts. Here's the complete story. Single-atom catalysts achieve the forbidden combination of homogeneous activity with heterogeneous stability and maximum atom efficiency. This enables transformative applications in transportation, energy, and chemical manufacturing. Single-atom catalysis beautifully illustrates how fundamental understanding at the atomic level translates into practical impact. By understanding electronic structure, coordination chemistry, and reaction mechanisms, we've created catalysts that seemed impossible just 20 years ago. This field shows the power of combining theory, advanced characterization, and clever materials design. It's a perfect example of how curiosity-driven research solves real-world problems. As we refine these materials and understand them more deeply, single-atom catalysts will play an increasingly important role in creating a more sustainable and efficient chemical industry.